Here's another even number one, number 32, but it's also a good one for a vertical asymptote example. So this integral says 0 to 1 divided by square root of 1 minus x squared dx. So you are supposed to notice when you do these problems that there's a vertical asymptote at one of those endpoints. And that's going to make it a problem that we have to take a limit to find. And these kind of problems, at first glance, you might not notice that, but you would have to look back at like all the Calc 1 homework sections to see that they never gave you any of these problems in those sections. They never gave you a problem where you had an endpoint that also gave you division by 0. But they didn't. They saved those all for this section, 7.8. And in real life, you just have to be careful. You have to look at the problem, and one of the things you need to check before you even do it is to see if it has division by 0 showing up. It's kind of a bad thing that they don't point that out as you're going through the sections in Calc 1. They just run out of time to mention all that. But it's true. You can't integrate things that have division by 0 as one of the endpoints or in between them unless you look at the limit. And for class, of course, like on a test, I would say, I would make a note of that so that you know you're supposed to use the technique from this chapter. But in real life, you'd have to like just double check that. So this one is actually fairly straightforward, but here's how the limit goes. You notice that, well, this side, first you have to notice that the 1, when I plug it in underneath, does give me 0. 1 minus 1 is 0, square root of 0 is 0, and I have a non-zero number over a 0. That's when you have a vertical asymptote. You remember, if it had a 0 over 0, it might just be a hole in the function. But non-zero divided by 0 is vertical asymptote. And here's what that looks like. 1 divided by square root of 1 minus x squared. If you plug in a 0, you get 1, because 1 minus 0 is 1. And then as you get closer and closer to 1, it's going to be a positive number underneath, because like if you plug in 0.9 squared, that'll be 0.81. 1 minus a fraction is still positive. 1 minus 0.81 would be 0.19 or something. Yeah. And so it'll still be a positive number, so it's a positive infinity that it goes to. So it looks like that. And actually there's no more graph. If you plug in anything bigger than 1, you get square root of a negative number. So that's the only graph that you have. It also does it on this side too. So there's the vertical asymptote. So we're looking for this area, which goes up to infinity, but it's still a finite area. It just gets small fast enough that you can actually bound it, that it never gets above a certain amount, even though it keeps on adding smaller and smaller amounts as you go closer and closer to 1. It never adds enough to get above the actual answer. And that is a kind of a paradoxical kind of a thing. It's very close to Zeno's paradox, which you have to look up, but you can answer by, say, take the limit. All right, so that's what we'll do here. Limit as t goes to 1, and in this case we do need to take t going to 1 from the left. So 1 minus. Can't take it from the right, that would actually give you square root of a negative number. So just from the left, 1 minus. And instead go 0 to t, 1 divided by square root of 1 minus x squared dx. Now we can take the antiderivative, and this time it's an easy one. It's one of the ones that we have memorized. Square root of 1 minus x squared. You could use trig substitution, but you'd quickly discover that when you use trig substitution, you get the same answer as the one that you have memorized from Calc 1. It might not be a bad problem to try trig sub on, just to see that it comes out this way. Yeah, what you get would just be, you would use the x equal to sine theta, and then quickly you get that this integral antiderivative is the inverse sine inverse of x. So I'll go ahead and write the limit so I can fit it in there easily. This is inverse sine, or arc sine, and I need to evaluate it from 0 to t. So that's the limit as t goes to 1 minus, and I'll have a inverse sine of t minus inverse sine of 0. And it helps to have the graph of inverse sine. This is the graph of inverse sine down here, arc sine. And it's just the graph of sine reflected through the diagonal line. If you look at the y equals x line. But remember, the graph of inverse sine, or arc sine, can only go between -1 and 1. Actually, that's a convention. It's chosen to go between -1 and 1. If you tried to draw any more of it, it would break the vertical line test, because it would have to look like the sine graph only on the y-axis. So it only goes between -1 and 1, and right here at 0, it goes through 0 just like sine does, and at 1, it's looking at sine from with your head tilted. It hits that's at pi over 2. So y is equal, or the output is equal to pi over 2. So I'm coming to 1 from the left. This is the 1 minus side of the limit. So that means I'm allowed to take that limit. The limit wouldn't exist from the left and the right, because sine inverse is only defined to the left of 1. And so I get the limit as t goes to 1 left of sine inverse of x. It goes to the point, pi over 2. So I get pi over 2 minus, and sine inverse of 0 is just 0. So pi over 2. And that would be what you get by plugging 1 into sine inverse as well, like on a calculator. But I needed to illustrate the fact that you have to take that left-hand limit, because sometimes you get different answers on the left and right, and you need to make sure you're looking at it from the left.